So today's problem. Determine whether the sphere x squared plus y squared plus z squared equals 8x minus 4y plus 8z minus 20 is completely inside a different sphere. X plus 2 squared plus y minus 3 squared plus z minus 2 squared equals 144. Now, looking at this, we look at the second equation and we say, that one, yes, I see that's a sphere. Easy to see, because it's of the right form. And when we have things in the right format, we're saying, okay, I can see what it is. In fact, we can go even further and we can read off things. For example, we can read off the center of this sphere. Well, the y-coordinate and the z-coordinate, straightforward. The x-coordinate, well, remember, the formula says x minus the x-coordinate. Here I have a plus. So the x plus 2, really we would think of this mentally as x minus negative 2. So this coordinate is negative 2. So there's our center, and our radius for our sphere, that we can easily see as a sphere. Well, this is the radius squared, 144. That's pretty nice. It's, well, of course, some people might say it's a little gross. Sorry, a little word humor. A gross is a technical term meaning a dozen, which means 144. So sometimes people will say, well, we need to order 12 gross or 10 gross. It means 144 is 1 gross. Okay, but the other equation, the first one, that's not of the same form. Now, it doesn't mean it's not a sphere. It just means it's not of the right form. Now, it might not be a sphere, but there's something that sort of hints at its spheriness. The thing that hints at the fact that it's probably a sphere is this combination of x squared plus y squared plus z squared together. And oftentimes when we see those three things together, we think sphere. All right, so we think it's a sphere. Well, what do we need to do? We need to rewrite it of the right form. So notice that in our equation, here there's only a single x, here there's a single y, and here there's a single z. So we want to put things together. So we're going to move things around. So I'm going to rewrite this. So this can be written as an example. I'll have x squared. I'll bring the 8x over. Then we have the y squared. I'll bring the negative 4y over. It becomes plus 4y. We have the z squared. And I'll bring over the 8z. And that, of course, all equals the constant that's left. So far, we haven't done anything other than group variables together. Now, our goal is we want to end up with squares. See, like x plus 2 squared, y minus 3 squared. Okay, so what do we need to do? Well, we just say, boy, it would be great if there were something that we could put in the gap here. Mind the gap. What can we put here so that this expression would become a perfect square? Okay, some people are saying 16. What's the technique that we need? Completing the square. That's the right answer. Complete the square. Now, the way to complete the square is if you have a x squared and then you have something x, that something is twice what you really need. Well, kind of. Okay. Side note. So if you look at x plus a quantity squared, perfect squared, that's x squared plus 2ax plus a squared. So that 2a corresponds to that negative 8. So if I want to know what a is, I divide by 2. Okay, so negative 4. Then I'm going to add a squared, so plus 16. So divide by 2 and square, and it becomes x plus a squared. What do I add here? 4. This becomes y plus 2 squared. What do I add here? 16. And this becomes z minus 4 squared. Now, there's a catch. You see, the problem is I've been now throwing in numbers. I've now changed this relationship, so I have to correct for what I've done. So to correct for what I've done, I need to somehow balance out. Now, there's a couple ways to think about it. For example, I could say I added 16, immediately subtract 16, life is good. An alternative way to say is, well, whatever I do on the left, I'll do on the right. So here I did 3 things. I added 16, I added 4, and I added 16. So I'll just do that on the right-hand side. So what we have is that the first equation is also a sphere, and if we rewrite it, that's x minus 4 squared plus y plus 2 squared plus z minus 4 squared, and that's going to equal 16. 16 plus 4 is 20. That cancels with negative 20. Okay, so in some sense, we'll call this the big one, because it has certainly a bigger radius. The small one, well, what is that? Well, the center. Where's our center at? 4, negative 2, 4. All right, what's the radius? 4. All right, good. So this is our small one. And what we wanted to ask is, okay, is the small sphere inside the big sphere? Now, one thing we could do is say, let's figure out every possible point on the small sphere and see whether or not it's in the big sphere. Now, the problem is there's infinitely many points. So that takes a while. So we don't want to do that. We want to do something a little bit faster. And so what we're going to do is sort of build up our geometrical intuition. And we say, okay, so we don't know what the picture is. Let's say here's our big one. Maybe, and you notice I'm not drawing spheres, I'm drawing circles. That's okay. Just think of geometrical, it's like, if I want to do a smaller case, let me try to get my intuition going with circles. Then my intuition can go up into 3 dimensions. So I have a big one, and I have a small one. Well, what do I look at? I look at the center, and I say, what's the furthest away I could be from the center? So if I can answer the question, how far away from the center of the big sphere can I get if I'm on the small sphere? Well, here we have an advantage. What we can do is think of it as 2 parts. I can go from the center of the big sphere to the center of the small sphere, and then I keep going, and how far do I go? I go the radius of the small sphere. Okay, so step 1, well, radius of the small sphere, that's 4. Okay, well, all right, radius of the big sphere, we should mark that down, that's 12. So now we have to get that distance. Well, that's distance between centers. What should we use? Distance formula. Okay, so the distance is the square root of, now you take the differences. So let's say 4 subtract negative 2, also known as 4 plus 2, or 6. So that's the difference in the x's. Add, now take the differences here. Negative 2 subtract 3. It's negative 5. Negative 5 squared. Take the difference here. 4 subtract 2. That's 2 squared. 36 plus 25 plus 4 gives us the square root of 65. Now, what do we want? Well, we want to compare these 2 distances. There's the 4 plus the square root of 65, and there's 12. Now, what do these represent? This is, if I want to be inside the big sphere, that's how far I can be away. This is the max distance from the center of the big sphere to the small sphere, just on any point. And I want to compare these 2 numbers. Now, one of 2 things happens. Either I have a less than or equal. If it's less than or equal, what's true? I'm inside. Or I'm greater than. What's true there? I have some of it outside. Maybe not very much, but a sliver. Now the question is, what's the truth? Now, here's a key thing. Square root of 65, that's not a square number. Is there a square number close to it? 64. So there's 8 squared plus 1. So is the square root of 65, how is that compared to 8? It's going to be a little bit bigger than 8. Because you took 8 squared, but then you went up a little bit. Okay, so 4 plus the square root of 65. How does that relate to 12? It's going to be bigger. Because I had 4 and then I'm going to add something a little bit bigger than 8. So it's like 12 plus a bit. Well, that's bigger than 12. So now we can answer the question. Is it completely inside the sphere? And the answer is no, it is not. It sticks out just a little tiny bit. In fact, we don't even know any point where it sticks out, but we know that there is some point where it does. And it would take us a while to find that point because it's not very much. So this picture is wrong, but that's okay. We use the picture to build intuition. And so intuition, that's a good thing. All right, well, that was a quick 10-minute problem. Whew. That's about how much time you'll get on each problem on the exam. Good times. All right, so let's talk about coordinate systems. So last time we talked about Cartesian coordinates. And they're the coordinate system that you probably are the most familiar with. It's a very nice coordinate system. But it's not the only coordinate system. So at some point you saw that there was another type of coordinate system that you learned about called polar coordinates. Now they work in different ways. So in Cartesian coordinates, you have a combination of distances. So I say it's a distance plus a distance. And these are how much you move in what we call the x direction, how much you move in what was called the y direction. And so with the pair of distances, I can locate where I am in two-dimensional space. In polar coordinates, it's a little bit different. What it is, it's a direction plus a distance, and the direction we call theta. And so what you do is you move off the positive x-axis in angle theta. That's your direction. Then you move forward your r. That's your distance. So if you've ever watched some old movies, maybe set on a battleship, you'll see that they have this exterior shot of this thing that's spinning around, and then they cut to an interior. It's a dark room. There's these kids with very thick glasses staring at the screen, and there's this little thing moving around. And occasionally you see a boop. There's a little dot on the screen. And then it gets a little closer, boop. That's radar, right? What's happening is it says, where are things relative to me? Because that's what polar coordinates are doing. It says, where is everything relative to where I am? I'm going to figure that out by saying, which direction do I go, and how far do I need to get there? So that's polar coordinates. Now, we can convert between the two systems by just saying, let's put them right on top of each other. So that's the picture here. You have x, y, r, and theta. And the nice thing is, we have a triangle. And it's not the wrong triangle, it's a right triangle. Right triangles are important. We almost always say, look, let's put everything in terms of right triangles. Okay, so we have a right triangle here. And now we start using some basic trigonometry. So for example, the cosine is adjacent over hypotenuse. And then we can say, aha, that tells us that x equals r cosine theta. Then we can say the sine, opposite over hypotenuse, y over r. So that says y equals r sine theta. Of course, Pythagorean theorem, x squared plus y squared equals r squared. And then tangent of theta equals y over x. And so these are our basic go-to formulas. Now, hopefully, among these, you really should have these down cold. You should just know them. X squared plus y squared equals r squared. X equals r cosine theta. Y equals r sine theta. If you don't, draw the picture. The picture will help you reconstruct. Now, there's a natural question. Why do we need two coordinate systems? Because we're not actually changing our space. To be perfectly clear, space is not dependent on how we describe location. Our description of location is a convenience. It allows us to bring algebraic tools and apply them to geometry. But it doesn't change space. It's still the same set of points. And so the question becomes, well, why do we need more than one way to describe things? The answer is, different ways to describe things have different advantages. So in some cases, it's very easy to describe something in, say, Cartesian coordinates, while in other cases, it's easier to describe things in polar coordinates. So that ability to pick the right coordinate system makes life better. We're going to see this particularly as we get towards the end of the course, when we're going to get to a situation where we're like, whoa, these are very complicated things to do in Cartesian coordinates. And then we're going to say, aha, but look, we have a better choice. Okay, there's an example. Sketch all the points, all of them, which satisfy x squared plus y quantity squared is equal to x squared plus y squared. Now, I would say that if you just saw that, your first reaction would be like, I don't know. I'm not sure what that looks like. In some sense, it's not a very good problem because it involves very high degree polynomials. There's going to be all sorts of crazy stuff going on. But there's probably something we can do. And of course, the idea is, well, we just talked about different coordinate systems. Let's switch over to polar. But there's something about this problem that's highly suggestive of polar. Is there anything you can see that says polar is a good idea? Yeah, this x squared plus y squared showing up, because x squared plus y squared in polar condenses. It simplifies. Our big goal in mathematics is to try to get to the point where we can say, we want things to be simple. A lot of people don't believe us when we say that, but we really do. Our goal is, let's make things simple. Let's make them understandable, and then we can make progress in solving the problems. All right, so we're going to go to polar. So the x squared plus y squared, that's r squared. What do we do with this y? Y equals r sine theta. Very convenient. We wrote that down. Equals, oh, that's all squared, equals x squared plus y squared is r squared. All right. Well, we don't need the squares anymore. We'll get rid of them. Okay, gone. R squared plus r sine theta equals r. Now what? Divide by r. Now there might be someone who might object, what if r equals 0? Let's hold that off. But let's suppose we can divide by r. All right, divide everything by r. R plus sine theta equals 1. Or, using our fancy subtraction tool, r equals 1 minus sine theta. Okay, that's promising. Now, we have to sort of figure out what does that mean. Now, our goal is to sketch this, and we say, okay, well, if we want to sketch it, we'll draw a little grid here. Let's see, I think I'll need something that looks roughly like that. And we just think about what this means. Now, if you're very familiar with polar coordinates, you'll probably recognize this. If not, we can just sort of figure it out. So oftentimes, what I like to say is sketching comes down to sort of connect the dots. And calculus, of course, is really good. It tells us which dots to connect, but we'll just keep it simple. We'll just pick a couple of convenient angles. For instance, theta equals 0. That's the positive x-axis. How far do I go? What's the value of r? 1. So let's say this is 1. All right. Now I come up, theta equals pi halves. So I plug in pi halves. What's the value for r? 0. So what's going to happen is I start, when I'm going in that direction, I'm going out a distance of 1. Then as I move my direction, I'm going to get closer and closer. When I come over in the positive pi, over here, what's r? So 1 minus sine of pi. It's 1 again. So it's going to, again, I start at 1, and we can start to draw it. And then as we move in, we get closer. It's actually going to, the closest it's going to be is 0. And then as I move out again, I'm going to start moving out. Now, suppose I'm down here, 3 pi halves. Sine of 3 pi halves. Do you remember that one? It's negative 1. What's r? 2. So you actually go out quite a ways. So you're going to increase up to hit the bottom. And it turns out 2 is as far as you can get. And then from that, you're going to start shrinking down again. Now, if you're not sure about that, one way you can convince yourself is if you say, well, I do know what just a function 1 minus sine x looks like. Do a little graph here. 1 minus sine x has the following shape. It starts here at 1, and it comes down, bottoms out, comes up to 2, and comes down again. So what we're seeing is we're seeing this phenomenon. 1, down to 0, back to 1, up to 2, back to 1. So that's the curve. That's the answer. And we're done. Now, I said, you might object, of course, you say, what about r equals 0? Well, we're okay, because notice that we hit the origin. That's r equals 0. Now, I have to say, I really like this problem, because it also serves as a friendly reminder. So we can just add a little bit of shading here, and then we can add the I love Calc 3. There you go. You know, show your passion for the subject. All right. Now that's 2D. We want to get up and go a little bit further. So we're going to go up to 3D. All right, so we're just going to put this up here, and we're going to start sort of talking about what's happening. So we already know about one three-dimensional coordinate system. That's the Cartesian coordinate system. And in Cartesian, what we have is 3 distances. Our 3 distances are the x distance, the y distance, and the z distance. So I just say, okay, I know how much I move in a direction which I call the x direction. I know how much I move in a direction called the y direction. And I know how much I move in a direction called the z direction. So every single point becomes a combination of 3 coordinates. Now we say, okay, well, let's sort of think about what we can do to generalize polar. Because polar said, pick a direction and then use a distance. Now there's 2 types of ways to generalize. One is to say, well, let's just do a very simple generalization. We'll call that cylindrical. So when you see cylindrical coordinates, you should really think of cylindrical as being polar coordinates plus z. And by that I mean it works by taking the polar coordinate system in the xy plane. And so when I'm down here, this, let me sort of quickly sketch where the xy plane. When I talk about the xy plane, I'm talking about the base here. So I'm here in the xy plane, and I can find my location in the xy plane, and then I have a z coordinate, or z, that tells me how far up and down I go. So what I end up with is that in the cylindrical coordinates I have a direction, and that direction comes from the same thing in polar. So that uses theta. Then I have 2 distances, r and z. Then we said, you know what? Let's try not just to do a simple add an extra coordinate. Let's really try to get the philosophy of polar. So the philosophy of polar says, first fix your distance. First fix your direction. And once you have a direction, that tells you where to go. And then go out in that direction by a fixed amount. And so what we're going to do is the third coordinate system, we're going to have 2 different directions involved. And then a single distance. So what are the 2 different directions? Well, they're angles. So angles are telling us how to set things. So how does it work? Well, there's a theta. And the theta does the exact same thing that theta does in polar. So there's a list here up top. Theta, that's the angle in the xy plane off of the x-axis. You'll see it in both cylindrical and spherical. It does the same thing. So theta tells me essentially what's happening is, if you can imagine like a turret, it's telling you how to rotate. So that's theta, is this motion here. Then there's a second angle called phi. Now phi is how far off you're going to come the positive z-axis. And we only use phi. If you see a phi, you automatically know you're in spherical coordinates, because that's the only time we're going to use it. Now you got to be careful here. It's the positive z-axis. So phi equals 0 is straight up. Then as we come down, we're increasing phi. When we hit phi equals pi halves, so where would that be? So phi equals 0 is straight up. If we come pi halves off, where are we? We're in the xy plane. In fact, the whole xy plane can be described by saying it's all the things where phi equals pi halves. So phi equals pi halves is this xy plane. Then we keep going. If we go straight down, that's phi equals pi. Now you might say, okay, where do we want to do if we want to go past pi? And the answer is we don't. We don't need to go past pi. Because remember, we have that second angle, theta. So I said theta was that rotation, turning. Phi is your elevation, moving up and down. Between those two, as long as you're allowed to make a full rotation with theta, so that's why we allow theta to go from 0 to 2 pi, and we allow phi to go from 0 to pi, we can look in any direction in three-dimensional space. So now, phi and theta have fixed our direction. The last thing is now to move out a distance. So the distance is called rho. So this looks a little bit like a p, but this is rho, spelled R-H-O. This is one of the great things you get to do in math, is you get to learn your Greek alphabet. Why did we choose that symbol? Well, because it's essentially the Greek version of r. It's doing the same thing. R is a distance, rho is a distance. How far out you're going from the center. It just depends on which coordinate system you're choosing. Now, one of the things that it's good to understand is, all right, what do these different variables look like if I fix them? So if I fix a value. So in Cartesian coordinates, it's not so bad. So for instance, suppose I want to understand, if I fix x, that says I come out a distance x, and when I say I fix x, that says the other variables can be whatever they want. So if I say fix x, y and z can be arbitrary. What shape do I end up with? Yeah, I end up with something very plain and simple. Okay, so this is x fixed. I move out an amount in the x direction, and that's it. Because this direction is the x direction. What if I fix y? What will I have? It will also be a plane. What I do is now I move in the y direction to where I'm fixing y. I fix y, and I'll get a plane. So we saw an example of this. Is like the xz plane is where y is fixed, but in that case y equals 0. You can be more interesting. Now, what happens? Excuse me. What happens if we fix z? It's still a plane. Yeah. So the Cartesian coordinates are very plain. That's all right. So if you have z fixed, you're going to get a plane. And essentially what it is, it's a plane that's perpendicular to the z-axis. As you move z, the plane will move up and down, but for any fixed value of z, it's a flat plane. Now, if you look at what you see here, what you can see is you get some very nice flat things. I guess that's one of the reasons why we love the Cartesian coordinate system. It's very good for flat things. And in particular, it's very good for boxes. Because it's easy to describe boxes in terms of the Cartesian coordinates. You just say, okay, where's the left side? Where's the front side? Where's the top side? They're all very easy to describe. Now let's talk about cylindrical coordinates. All right. Well, one of them is pretty easy, and that is z. And the reason z is easy is z does the same role in both Cartesian and cylindrical. It's the same thing. It measures how far off you go from the xy plane. So when we talk about z, we're going to end up with the plane again. So that's z. Now, let's pick another one. Suppose we fix r. R equals 2 or something. What will r equals 2 look like? It's a cylinder, that's right. So think about what r does. If I think of it in terms of the xy plane, I have the origin, and R says how far out you move from the origin. So if I fix R in the xy plane, I'm going to form a circle. But notice I haven't said anything about z. So take that circle and move it up and down. So what you're going to end up with is you're going to end up with a cylinder. So R is a cylinder, and the center of that cylinder is the z-axis. This is R fixed. Now, by the way, notice the name cylindrical. Cylinder. That sort of gives you a suggestion. See, cylinders are very nice in cylindrical coordinates. All right. Well, there's one other thing to talk about, which is theta. All right. What does theta fixed look like? That one's a little bit more subtle. It does look like a plane, but I would say that we should argue it's a half plane. So what you do is you go out some angle theta. Let's say here is our angle theta. And we get a half plane going out through space. So as theta varies, we're basically sweeping out space in this half plane as we sweep around. So there's our theta fixed. Now, when it comes to describing things, what is cylindrical really good for? I would say that cylindrical, you want to go to cylindrical when you have the following. If you have symmetry around the z-axis. And when I say symmetry, I mean you could say, pick your picture up, you can spin it around the z-axis, it doesn't change. That's really good for cylindrical coordinates because it's built up to have this nice symmetry built into it. All right, now we get to spherical coordinates. Now, the good news is we actually know what happens for theta because, again, theta is the same for both systems. So theta is this half plane. All right. So there's theta. Let's talk about phi. Suppose I fix phi. Now phi is an angle, so we're talking maybe like phi equals pi thirds or phi equals pi fourths. What will that look like? Well, it's a cone. Oh, you guys are fast. So what's happening here is phi says how far off do you come from that positive z-axis? Now remember, we're fixing only the phi. Phi is fixed. So rho says I can come out any direction, and theta says I can spin, because it can be any angle. So if you just think about coming off the positive z-axis and then spinning around because theta is arbitrary, you'll see that what happens is you spin out and you get to form a cone. So this is an example where phi is fixed. So as phi varies, we're going to form cones. Phi equals 0 is actually just the positive z-axis. Then we sort of open up a cone. It's like opening up an umbrella. So as we increase phi, the umbrella opens. Then maybe it's a really windy day. The umbrella turns inside out as we go past pi halves. And then eventually when we get down to phi equals pi, negative z-axis. The last one is rho. All right, what does rho do? Well, rho says it's a distance. So it's a distance from the center, distance from the origin. So I'm fixing my distance to a center point. So I want all the distances which are that distance away. What shape am I going to have here? Exactly. It's a sphere. Now, there was a clue. Notice the word, spherical. So that's a clue that we should be getting a sphere. And so, yeah, so if you fix rho, so rho fixed will form a sphere. Now, what is spherical coordinates useful for? Well, spherical coordinates are very useful for what I would say are spheres. That's sort of the big clue. If you have things which have spheres and cones, spherical coordinates are fantastic for that. And anything where you have symmetry around the origin, that's also a good time when we pull out spherical coordinates. We'll see examples later on in the semester. We won't use much of the coordinate system until later in the course, but it's good to sort of plant the seeds now so that we understand. We start building up our intuition here. All right, so those are our three coordinate systems that we're going to have. Okay, well, again, same thing we said with 2 dimensions. Look, the different coordinate systems don't change space, because that's not changing. What's changing is our description. So that means that we can move back and forth between the coordinate systems. So, how do we convert? The answer is we just put everything on top of each other, and we say, how do they all fit together? And once we do that, it just pops out really quick. So here's a couple of things that we can spot right away. The x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared. This part right here, that's polar. So those we already know. That's pretty simple. Now the next one, rho squared equals x squared plus y squared plus z squared. Well, again, here's our point. We can describe it in terms of x, y, and z. So this is our point. If I label it using the Cartesian coordinates x, y, z. Now, if I want to know rho, rho is the distance to the center. In our case, the origin. We know the distance because we have the distance formula. It was basically built off of the Pythagorean theorem. So we can say that this distance squared, which is going to be rho squared, is the x squared plus y squared plus z squared. So this formula, this is our distance, which follows from the Pythagorean theorem. All right, so far, so good. Well, that's only a part of them. All right, let's talk about the next ones. Z equals rho cosine phi, r equals rho sine phi. Now, here's the trick. Look at the triangle. Now, it doesn't look like it, but that's just because of our angle. What's true about the angle here between this line segment in the xy plane and this line segment coming up off the xy plane? It's a right angle. Because if I'm coming off of the xy plane, I'm perpendicular to it. That's where z goes. It's perpendicular to the xy plane. So again, we have the right kind of triangle. Now this angle phi is actually not in the triangle. However, fun fact, you can use your geometry. This angle here is also phi. Now the way you can see that is that these two angles, phi and this angle here, are what are called complementary. They like to complement each other. My goodness, phi, that's a wonderful hat you got. Well, thank you. Thank you. All right, so they're complementary angles. But these two are also complementary, and therefore it must be that these two are the same. Okay. Well, now that you have a triangle, the rest is pretty straightforward, because you know the hypotenuse is rho, the adjacent is z, and the opposite is r. So if you use some basic trigonometry, just like we did when we did x equals r cosine theta, y equals r sine theta, we can see that z is rho cosine phi, because z is the adjacent side, and r is rho sine phi, because that's the opposite side. So this follows from your trig. Now, the last two look kind of like, ugh. Now, you don't have to make the sound, but you could if you wanted to. The good news is, I don't memorize these. So you don't have to memorize them either. How do you figure it out, though? Well, here's the cool fact. Notice that these two things have rho sine phi in common. What is rho sine phi? R. Right? So come over here. Replace r by rho sine phi. Then you have rho sine phi cosine theta. There you go. Replace r by rho sine phi in this other equation. Y equals rho sine phi sine theta. There you go. So what happens is this basically is a combo. It's a combination move. You combine some facts together. So I would say these two are not going to be heavily used. The remaining you should know, because of course you came in knowing polar, because I trust you. You passed your previous courses. That means you know polar. And then that means you only have a few more facts to pick up. Now we can move between coordinate systems, and so let's try that out. We're given the point 1, 1, root 6. And now, because of the format here, this is implicitly saying that this is Cartesian. Because Cartesian coordinates are the ones that come in triples. I will say, and I do apologize, I forgot to mention this before, one small note, and I apologize to you engineers that have to suffer for this. There are some engineering topics where in spherical coordinates, what we're calling phi, they call theta, and what we're calling theta, they call phi. I apologize. The engineers got it wrong. But you're just going to have to learn to adapt. But anyways, okay. Sidetracked. All right. So, but there isn't sort of a canonical way to write the other coordinate systems. So we don't, write like r theta z. We just say, okay, this point is r equals that, theta equals that, z equals that. So if you ever see a triple, like in parentheses, like you do here, that means Cartesian. Okay, so we're in our Cartesian coordinate system. 1, 1, root 6. All right, so what do we want to do? We want to change it to cylindrical, and we want to change it to spherical. Well, probably it's easier to start with cylindrical. Because with cylindrical, what do we need? We need r, we need theta, and we need z. Now the good news is, in cylindrical, it matches the same z. So z is root 6. And if I want to know r and theta, I can just go into the xy plane. So r and theta, well, here's the point 1, 1. So r is the distance, and theta is the angle. Do we see what angle we formed here? It's okay if you want to say with degrees first. Yeah, 45 degrees. And now that we know 45 degrees, what is that in terms of radians? Pi over 4. So our angle is pi fourths. Now r, well, Pythagorean theorem, because you can think of 1, 1. So 1 squared plus 1 squared would be 2. So the r would be square root of 2. All right. So there is r, theta, and z. Okay. Well, that was good. Now let's talk spherical. Now the good news about spherical is we have our three angles. We have, two angles, theta, phi, and then we have our distance, rho. One of them is a freebie. Which one is a freebie now? Theta. Theta is a freebie because theta does the same thing. So if you have it for Cartesian, you have it for spherical. All right, what's another one that's not going to be too hard to figure out? Rho. Yeah, rho is fairly straightforward because you have the distance formula. So what we can do is we can say rho squared, that's x squared plus y squared plus z squared. All right, so that's 1 plus 1 plus 6. So that says rho squared is 8. So what will rho be? Square root of 8. Also known as 2 root 2, because 8 has a factor 4 I can pull out. All right, 2 down, 1 to go. Phi. Well, what can we do? Well, the answer is we can use some facts that involve phi. So I'm looking here at these equations. Z equals rho cosine phi, or R equals rho sine phi. Do you have a preference for which one you want to look at? Okay. Well, let's start with the top one. The strong, overwhelming vote. Okay. So Z equals rho cosine phi. Now, the good news is we know Z, root 6. We know rho. We just computed it. 2 root 2. Cosine phi, we don't know. But, good news, root 6, that's square root of 3 times square root of 2. The square root of 2's can cancel. So we end up with saying that cosine of phi is equal to root 3 divided by 2. Now that's not phi, but that's the cosine of phi. And so we started thinking, is there some angle, phi, that we hopefully remember from trigonometry, where the cosine of that angle is the square root of 3 over 2. And what angle does that? Pi over 6. And there we go. All right, good. So we were able to switch between the two coordinate systems. All right. Now, it's good to know some common surfaces. So I'm just going to point some of these out. So suppose you have a sphere, and we have to change the name of the radius because r means something now. Radius is tau, centered at the origin. Well, in Cartesian coordinates, it's x squared plus y squared plus z squared equals your radius squared, tau squared. In cylindrical coordinates, well, the x squared plus y squared becomes r squared. So z stays z, so r squared plus z squared equals this radius squared, tau squared. And of course, spherical coordinates, well, now we're in the right setting. Spherical coordinates, we use spheres. So rho equals tau. Again, you can see there's a difference. Spheres are great in spherical coordinates. What if you have a cylinder? Well, cylinder, x squared plus y squared equals tau squared, because what it is, it's a circle that just doesn't have any z part to it. So that's not too bad. But again, that's in Cartesian. If you switch to cylindrical coordinates, all of a sudden, beautiful. Rho equals tau. Elegant, elegant. What about spherical? And it's like, whoa, that doesn't look elegant at all. Rho equals tau cosecant phi? Where did that come from? Well, it came from recalling that when you switch, r is rho sine of phi. So if we have that rho equals tau, that says rho sine phi equals tau. And now solve for rho. Cosecant is 1 over sine. So you can see, okay, again, there's a clear winner. Cylindrical is clearly the best. And in cylindrical, well, we have to make compromises. How about this one? The upward opening cone, the tip is at the origin, and it forms an angle of pi over 4. So this is a cone that we're going to see in a lot of examples. There's lots of cones. We can adjust the cone by doing various things. So in Cartesian coordinates, z equals the square root of x squared plus y squared. Okay, that's not so bad. In polar coordinates, z equals r, and in spherical, it's pi fourths. So again, cones are actually pretty easy. In fact, they're easy in both coordinate systems. Now, quick comment. Y is equals r. Well, notice that there's really no theta component because it doesn't depend the angle you pick. And if it doesn't depend on the angle, what you do is you can switch to what I like to call the RZ plane. And so that just says, it's not like we're going in one particular direction. We're just saying go a generic direction. We call that R. And then we have our up-down motion, Z. And we say, well, what does the cone look like? Well, the cone, if I look in the RZ plane, it's like I'm looking at just sort of a slice where I pick a theta. When I slice, all I see is a line segment. So this will become a cone once we spin. And all you have to figure out is what's the right line segment. In this case, it's the line Z equals R. So identify and sketch rho equals 6 cosine phi. Now there's a couple of clues right away. The rho and the phi. Those are names that we associate with spherical coordinates. So even before we start, we know that, okay, we're dealing with a spherical coordinate type situation. So we start thinking, okay, all right, what do we know about spherical coordinates? Now for us, the thing is we don't know very much. We're really trying to build up our intuition right now of spherical coordinates. So one idea is to say, well, where are we successful in identifying things? And the answer is we're really successful at identifying things in Cartesian. Now that's not because Cartesian is necessarily the best way to describe something, but rather it's just a level of familiarity. So okay, so given that we understand Cartesian coordinates, we say, okay, let's see if maybe what a first step should be is instead of writing it, instead of trying to sketch it, instead of trying to identify it, is we convert. So here, let's go back to our converting. So we have rho equals a cosine phi. Now, looking at our equations, there's this expression right here that involves a cosine phi. And we see that, aha, if we can get a rho cosine phi, that's equal to z. So we say to ourselves, great, there's not a rho there, so what do? And the answer is, we put one there. But we have to do it in a way that's legal. It's like a legal move. So one way we can do it is multiply by rho. But if we do it to the right-hand side, we also need to do it to the left-hand side. So we have rho squared is 6 rho cosine phi. And aha, that we said was z. Now we say, well, what about this rho squared? Well, if you go back to our list here, we actually know something about rho squared. That's x squared plus y squared plus z squared. And therefore, we say this becomes x squared plus y squared plus z squared. And now we say, wait a second, this reminds us of something we talked about earlier. When we see x squared and y squared and z squared together, we think spheres. So now we think this is a sphere. So all right, so it's a sphere. So we need to do what we did before. Well, put all the variables together. Now there's only a single x, there's only a single y. Move the 6z across. And so we have x squared plus y squared plus z squared minus 6z equals 0. Complete the square, so divide by 2, negative 3, square that, plus 9. Do it on both sides. And we get x squared plus y squared plus z minus 3 squared is equal to 9, which means that we know what this is. This is a sphere. In fact, we know a little bit more. The center is going to be at 0, 0, 3, because we can read off 0, 0, 3, and the radius is going to be 3. All right, well, what does that look like? So here we have our x, y, z. The center is moving up the z-axis, so we go up to 3. Let's say that's 3. The radius is 3. So the radius is going to go down here, come up here, and now we have our sphere. In fact, what it is, it's a sphere of radius 3 that's sitting on top of the xy plane. In fact, it's nestled right there at the origin. So there's our shape. There's our sphere. All right, that's not so bad. Well, I think we have one more. All right, what's our last problem? Sketch the region consisting of points satisfying 0 less than or equal to phi less than or equal to pi fourths and 0 less than or equal to rho less than or equal to 2. Also, express this region in terms of cylindrical coordinates. Now, let's think about this as saying, look, there's two things here. We have a 0 less than or equal to phi less than or equal to pi fourths. Now, phi measures how far off we are from the positive z-axis. So phi equals 0, that's straight up. And then we're going to keep opening up until where? Well, until we get to a nice angle of pi fourths. All right? And so what's our set of points? So if we only have 0 less than or equal to phi less than or equal to pi fourths, it's anything that's on or above this cone. So it's all these points here. All right, so there's that region. Well, all right, but that's not the full answer. Because remember, we also have a second condition. 0 less than or equal to rho less than or equal to 2. So what does that look like? Well, that says the following. The rho, that's our distance to the center. So the center being the origin. So I want to go out, and I want to be distance 2 away. So I can, as long as my distance to the center is at most 2, I'm good to go. All right, so what do we have? Well, that's going to be a sphere. In fact, it's a solid sphere because we want to be from 0 all the way out to 2. So now what's our last thing? Our last thing is to say, hey, we see the word and. Now when we see the word and, what that means is that both things have to be satisfied. So it's like you're going to cross your eyes. So what happens if we cross our eyes? What do we see? Well, we have to be in the sphere, but also in the cone. So what's going to happen is we're going to be part of this cone going up, but we're not going to go up very far because we're going to hit the top of the sphere. And so it's going to look something like that. So here we see the top of the sphere. This is the sphere, radius 2. On the side, we see the cone. And now it's everything in there. It's kind of like you have like an ice cream cone, and you've been working your way, leveling it off, get a nice circular top. All right, so there's our answer. That's the answer to the first part. It's our sketch. Now, there's a second part. Express the region in terms of cylindrical coordinates. Now, cylindrical coordinates do what? Well, we need to have theta, and we need to have r, and we need to have z. Now, one of the things is that spherical coordinates and cylindrical coordinates match in their thetas. So whatever the theta was doing before in our spherical, we know it was spherical because of the phi and the rho. So whatever theta was doing before, it's still doing. But you might say there was no theta before. Well, that means that there was no restriction on theta. So here, our conclusion is theta is going to be arbitrary. And usually the way we indicate that is we don't include any theta. So that means that we're going to have this nice rotational symmetry around. All right. So how do we then get a handle on it? Well, looking at our shape here in the middle where they overlap, again, we have this nice rotational symmetry around the z-axis. What we can do is we can look at a slice. And now what we're slicing here is we have the z-axis, and then we have r. So I'm not slicing in like the x, or I'm not slicing in the y, I'm just saying, look, it doesn't matter which slice I'm in, so I'll work in what I like to call the RZ plane. How do r and z relate? So let's think about these shapes. Here, the cone. What does that look like? What does that look like in the slice? Well, it's the cone that comes off the positive z-axis at a 45-degree angle. So this is what the cone becomes. It's a line, pi fourths, or this angle here, pi fourths. Now, if we want to describe this line, that's not a very hard line to describe. Because what is it? Well, it's the line coming out. This is going to be z equals r. All right. Then there's the top part, that sphere. So when we take a look there, what we're going to see is that sphere is a part of the circle. So here, that's our sphere. Now we have to think about, well, what does that become? And the answer is, well, what's the formula for the sphere? Shade that in. The formula for the sphere, you have x squared plus y squared plus z squared equals 4, 2 squared. Now, we want to be in cylindrical. X squared plus y squared becomes r squared. So r squared plus z squared better be equal to 4. Or solving, we can say, look, z squared is 4 minus r squared, or z is the square root of 4 minus r squared. All right. So this is z equals the square root of 4 minus r squared. Now there's a question, okay, if we were going to describe this in terms of cylindrical, what would we do? Well, we say, look, theta is arbitrary, and now oftentimes what we do is we want to express r in terms of z. So we can say the following. We can say that r is less than or equal to z, which means that I'm above the cone, and I'm less than or equal to the square root of 4 minus r squared, which means I'm below the sphere. In fact, that's actually enough. Just that information will do it. Now, you might want to say, well, can we go a little bit further and say, what's true about r? Well, we can. So if I want to know where r goes between, I can try to figure out, well, where do these intersect? Well, wherever they intersect, it has to be the case that r and z are the same. So if I come down here and say, well, look, if r and z are the same, then that has to be that r squared plus r squared equals 4, or r squared better be 2, or r equals the square root of 2. So we could add in the following 0 less than or equal to r less than or equal to the square root of 2, but it's redundant information that actually is forced on this relationship. You might wonder, well, wait a second, do we need to assume that r is greater than or equal to 0? And the answer is maybe. And the reason I say maybe is it depends on what convention you're following. The general convention is that we're going to say that r is greater than or equal to 0. Similarly for rho. There are some times where we'll relax and say, well, here's how we'll interpret it. So we could include some more information, but this is good. This describes it. All right, well, that wasn't so bad. In fact, really, a lot of this is just saying, how do we think about things? How do we describe things? And don't say, look, let me jump right to the answer. Think about the individual pieces. What are the parts? How do the parts fit together? And how can we see the whole? And once we got that, life is good.